hit in that geometry, the two moons are separated by about as much as possible.
All right. Back to the media for our next question, please.
Thank you. As a reminder, if you'd like to ask a question, please press *1 and record your name when prompted. The next question comes from Morgan McFall-Johnson with Insider. Your line is open.
Hi, thanks so much. Can you just talk about the strategy once DART is over? How do you get to the point where you're prepared to effectively use this method on an actual hazardous asteroid? Do you need to follow up and do another test mission like this one eventually? And just as a follow-up, is this the kind of thing where you build a DART-like spacecraft and have it on standby, or do you have to custom build a spacecraft once you discover a particular hazardous asteroid, and how long do you think that would take? Thank you.
I'll pass to Lindley.
Yeah, I'll take that. Well, this test is to demonstrate that this technology is mature enough so that it would be ready if a actual asteroid impact threat was discovered. So after this mission, and we've analyzed it, assuming we don't have any major surprises, of course, we think that this technique would be then available, would be a part of the toolbox that we're starting to build of capabilities to deflect an asteroid. In studying all the different kinds of scenarios we could be faced with, the orbits of these bodies, the time that they could be discovered ahead of the impact, the velocities that they may have. We know that we need a toolbox of capabilities. No one technique, just kinetic impactor, may not be applicable in all the situations. So after we do this test for kinetic impactor, we'll want to do tests of other techniques, like a gravity tractor, for instance. Gravity tractor is you just station keep with a spacecraft off to the side of an asteroid, and nature's tug rope, gravity, will slowly pull that asteroid off the impending trajectory. Other techniques, ion beam, laser ablation, there are a number of good ideas out there that we would want to look into subsequent to DART. But the message is that our strategy is to have a toolbox of several different techniques after many years of testing different things. Luckily, asteroid impacts don't happen all that often, and so I think we have time to do these kinds of things. And we never know what the technology may be in the future when we are actually faced with an asteroid impact. We might have tractor beams and other types of technology that would be more appropriate at that time. This is just a start.
And Lindley, can I jump on
Sure.
and just say a couple of things also? Because DART is demonstrating some of the other technologies, things like the NEXI ion engine, for example, is a good way of getting to a variety of asteroids because you are providing a lot of really low thrust to the spacecraft. So you can actually maneuver around asteroids much more easily than you would with a traditional system where you're burning through a lot of propellant and you're using less propellant for that. So these are the type of things that we are actually demonstrating that might come in handy in getting to a variety of different asteroids, no matter where they are.
Thank you so much. We are going to go back to a social media question now. Nicole Choi from Twitter asks, how will DART find and hit the asteroid? Elena?
Good question. Thank you, Nicole. So we are going to be using optical navigation for a portion of the cruise where we used our telescope called Draco. And this telescope is going to be searching for Didymos the whole time. We are in space. We're really for real, starting about 40 days out before we impact. So right now we have a pretty good understanding of where Didymos system is. And so when the spacecraft gets launched, the rocket puts it on a particular trajectory to go to Didymos. And in fact, if everything went well, if we're on a perfect trajectory, we wouldn't have to do any maneuvers at all. So we're going on our trajectory, and about 40 to 30 days out, we're going to start searching for Didymos, where we expect it to be. And the whole time, 40 days out to about 10 days out, we are taking images every 5 hours, and we're processing them on the ground here with the navigation team at JPL, who's actually processing images and making sure that we're navigating towards Didymos correctly. And we are still navigating to Didymos all the way in through 4 hours in, at which point the spacecraft starts navigating itself. And at that point, it keeps navigating itself to Didymos until about an hour out, at which point it switches. It finds Dimorphos, because as Andy said, the moon will come out from behind Didymos. It finds Dimorphos, and then it navigates towards itself, Dimorphos. But the whole time is just based on the fact that we're taking pictures, and we know where it is.
We're going to go back to the media now. Operator, do we have the next question?
Yes, our next question comes from Paul Brinkman with UPI. Your line is open.
Hi, yeah, thank you very much. Can you hear me?
Yes, we can.
Great. One quick question about the impact timeline. The mission website says September 26th to October 1st. How does that change if the launch day is delayed? And then I also wanted to know, I guess there was going to be secondary observation by radio telescope, and Arecibo was part of that plan. Can you just explain what, if any, impact the collapse of Arecibo had on that plan? Thanks.
Thank you. Elena.
I'll take the first half of the question, and then I will throw it over to Nancy. Yeah. Yep. Sounds good. So the reason why it says September 26th through October 1st is it all depends on when we launch in the launch period. As I said earlier, we have 84 opportunities. If we launch on day one of our opportunity, we will hit Dimorphos on September 26th. And basically, as we go farther in a launch period, by February 15th, we're hitting it on October 1st. That constraint was really placed there just for the radar observations too, so that way the radar can actually see when Dimorphos is closest to Earth. So Lindley, over to you.
As we've said earlier, the real measurement of the change in the orbital period of Dimorphos about Didymos will be done with optical telescopes. It's done by observing the light curve brightness and dimming of this eclipsing binary when the moon goes in front and behind the primary object. So radar was never a prime requirement for the mission. That being said, it's always good to get radar observations because they provide very precise positioning, and if the signal is strong enough, actual imaging of at least the main body and maybe the position of the moon. A moon that small, that far away, over 6 million miles, is still hard to detect with our planetary radar. Yeah, we still grieve the loss of the Arecibo radar, but we still have Goldstone, 70-meter Goldstone solar system radar capability, and we do plan to observe using Goldstone, and if the setup is right, we'll use the Goldstone to transmit, the 70-meter to transmit, and we'll receive the signal at the Green Bank Observatory in West Virginia. That setup, that bistatic radar setup, gives us the strongest signal-to-noise ratio and would provide the best observations in this particular situation.
And we'll take the next media question, please.
Thank you. As a reminder, if you'd like to ask a question, please press *1 and record your name. The next question comes from Michael Greshko with National Geographic. Your line is open.
Hi, thanks so much. Two quick questions. I think the first might be for Nancy and Andy. The second is for Lindley. there's been some questions about the long-term characterization of DART's effect. I was wondering if you could speak to how important the European Space Agency's upcoming Hera mission will be to understand the long-term impact of DART. And then for Lindley, you mentioned earlier the importance of detecting these asteroids as soon as possible. Earlier today, the Astro 2020 Decadal survey was published, and it noted that satellite megaconstellations' biggest potential scientific impact on astronomy would come into play in the discovery of near-Earth objects. So I was wondering if you could speak to kind of the long-term plan for observing and detecting near-Earth objects and the potential effects of things like megaconstellations. Thanks.
Great. We will go to Andy for the first question and Lindley for the second.
Okay, so the European Hera mission will launch in 2024 and will visit Didymos system in late 2026 and make very important contributions to understanding the outcome of the DART impact. So there's two main things it would do. The first is the spacecraft, the European spacecraft Hera, will directly measure the mass of Dimorphos. That's a measurement DART cannot make all by itself. We can make estimates, but there will be a direct measurement of the mass from Hera in rendezvous with the Didymos system. And the second important measurement they'll make is they'll be able to study the impact crater that the DART impact made. How big is it? How deep is it? And maybe even look for pieces of the DART spacecraft that may be left sticking out of the ground. Who knows?
Okay, well, the second part of that was what's going to be the impact of these mega constellations that are being talked about of 30,000, spacecraft, something like that, to these surveys, the ground-based surveys. The first thing is that, the current surveys, there are spacecraft up there now, satellites, debris, and it is something that we have to contend with our imagery from the ground already. But with that size of constellation, doing some estimating on some of our survey systems, the number of times that one of those spacecraft would be in the field of view when you've got that many up there, and just about every image that we would take would have one of those spacecraft in it. And so a part of the image, now these are very wide field images, so only a part of the image would be damaged, so to speak, by that satellite being in it, but it wouldn't completely disable the capability. But our real direction for the NEO program is our next mission that is under the formulation right now into preliminary design, and that is the Near-Earth Object Surveyor, which is a space-based IR infrared telescope that's being specifically designed to detect, track, and characterize near-Earth asteroids. It will be launched and positioned into space at the Earth-Sun L1 point, about 1 million miles sunward, and that'll be well away from Earth and won't be affected by these constellations. But it's still a area of concern because a lot of our characterization observations, and certainly a lot in the astrophysical realm, that still use the ground-based observatories, are concerned about the number of spacecraft that are up there and what effect they could have on the imaging from ground-based telescopes.
Thank you so much. We are going to take another social media question now. Steve from Facebook asks, what is SmartNav and how does it work? I think that's for Elena.
Thank you, Steve. All right, so SmartNav is a set of algorithms that we use in order to be able to find and hit Dimorphos. And these algorithms come from the development for many years at the Applied Physics Laboratory for missile defense, where they also look for really small things and they try to hit them. But in this case, we're using it for planetary defense. And it's a set of algorithms that control our thrusters, which are a main way to propel our spacecraft. They control our attitude to make sure that we can actually point our imager at the asteroid. So we're pointing our imager at Dimorphos, we're taking pictures, and those pictures add up in the spacecraft, and they're processed to see if we can form a track to that asteroid. You know, we basically are taking out the attitude motion of the spacecraft, and we're trying to see if we can keep tracking that one dot that we think is the asteroid. And that's how it basically works. At some point, it switches over to Dimorphos from Didymos, and does the same thing the whole time. It's trying to correct its attitude and correct its trajectory. You know, so it centers itself in space and figures out, where am I? Where do I need to go in order to be able to have, you know, to really directly hit this dot?
Yeah, the main thing, it has to take into account orbital motion too,
Yes,
in addition to just linear flight.
That's right. That's right. The fact that the Dimorphos is not just going back and forth and you're seeing a 2D image of it, right. That adds up as well. As well as stars popping in and out of the field of view of the star tracker. Yep. You know, it's a little bit more complicated, but that's the basics.
Well, thank you so much. We will go back to a media question now, please.
Thank you. The next question comes from Megan Bartels with Space.com. Your line is open.
Thanks so much. This might be sort of a basic orbital thing, but could you explain why if you hit Didymoon head on, it will speed up the orbit instead of slow it down? Thanks.
All right, we'll pass to Andy for that one.
Okay. Yes, when we hit Dimorphos head on, instantaneously you are slowing down the moon in its orbit. But because it's slowing down, what happens is that the centrifugal force that's holding the moon away from Didymos' gravity, the centrifugal force is reduced, and so the moon falls closer to Didymos. When it falls in closer, it speeds up. This is the same process as the skater who's turning, pulling in her arms, and she spins up faster. It conserves the angular momentum. So the same process, Dimorphos coming in, swinging in closer to the main body, it has to speed up to conserve angular momentum. Of course, when it goes back out again in its orbit, it slows down again. But the speeding up is more than the slowing down. And on the average, the orbit period is shortened, and on the average, the orbit speed increases. So that's what happens. Even though we hit it head on and instantaneously slow down the target.
Thank you. The next media question, please.
Next question comes from Marcia Smith with SpacePolicyOnline.com. Your line is open.
Thanks so much for letting me ask a second question. Someone brought up earlier about how the astrophysics decadal survey is out today, and it makes me wonder about the planetary science decadal that's underway. Are they evaluating planetary defense missions and how you should prioritize the type of techniques that you have, you know, apart from kinetic impact, and to help you prioritize where you should be investing your money for future missions? And if that's not part of the decadal, is there some other group within the academies or somewhere else that helps you prioritize whether to invest in these kinds of missions or invest in, is it NEO-SM, the survey mission, or ground-based identification of asteroids? How do you sort all that out? Who is it that advises you?
Well, we happen to have the perfect person to answer that question here, and that is Nancy.
That's not the intro that I was expecting there, Lindley. Yeah, I'm serving as the chair of the Small Bodies Panel for the Planetary Decadal Survey that's currently ongoing. We've had a number of open sessions, and you can check out the website for there. But yeah, planetary defense is within the scope of the Planetary Decadal Survey for the first time. So this next Planetary Decadal Survey that comes out will include a discussion of planetary defense and priorities looking forward for the next decade. Obviously, that's not scheduled to come out until next March, so I really don't have a whole lot more to say about that, but if you want to add on to that, Lindley, I think it's really great that planetary defense is being included in the Decadal survey for this time.
Yeah, it is, and it signifies that the planetary defense program is a important part of the overall planetary science portfolio at NASA now.
We do have one last social media question. I think if we answer it quickly, we can fit it in before we have to go. Sharon on Twitter asks, do we already know what kind of surface Dimorphos has? And if it turns out to be a porous surface, would the redirection still be effective?
Okay, do we already know what kind of surface Dimorphos has? The answer is no. Simple as that. We know nothing about it. It's just barely resolved, even in the radar data. And will the redirection still be effective? Yes, we believe so. The amount of deflection we get is uncertain. Porosity affects that, but there will be a redirection. We are confident of that.
Thank you so much. Thank you to all of our speakers for being here today. Thank you so much for joining us. Keep watching nasa.gov/live for that launch coming up later this month. And in the meantime, thank you. Goodbye.